Hello, and thanks for joining our webinar today, Containment Aisle Fire Detection Leading Edge Practices and Misconceptions. Our presentation today focuses on fire detection solutions for air containment aisles. And during this presentation, we'll introduce and discuss fire detection goals, high-density cooling strategies, containment aisle configurations, detection selection criteria, aspirating smoke detection technologies, coverage strategies, detector selection, and we'll wrap up with a summary. Before we begin, just a quick introduction as to whom Xtralis is. Xtralis is in the business of manufacturing detection, and this is the core of what we do, and it's what we're best known for. Our main objective is, and always has been, to detect smoke without compromising the early warning capabilities of our products. We are the original pioneers and innovators of very early warning air sampling smoke detection technologies, and today we're recognized as the industry leader. With over 3 billion square feet of critical infrastructure protected today by our leading brands VESDA, ICAM, OSID, and our portfolio of security products, we've held true to our commitment to perform up and beyond, setting the standard for very early warning. So now let's switch gears and talk more specifically about the subject of our presentation today, and begin by discussing high-density cooling strategies, and more specifically air containment aisles. So as opposed to other types of heating, ventilation, and air conditioning HVAC systems, data centers are designed for computers as opposed to people. The heat that needs to be removed is generated by the continuous operation of IT equipment, which must be removed for proper operation of the data center. So hot aisle, cold aisle configurations, which has been in the industry standard, is no longer a viable solution as power densities have significantly increased, outpacing improvements in HVAC technology. Air containment aisles improves airflow management within a data center by focusing cooling to the more narrow scope of cooling individual components, as opposed to the wider scope of cooling the entire room. It's this cooling technique has been proven efficient and effective at reducing cooling cost, and today is really the norm. Automatic detection plays an important role in the overall fire protection strategy, often providing first line of defense. So before we begin planning our fire detection design, we need a clear understanding of performance goals that are to be achieved, variables that may impede meeting performance objectives, selection of detection technologies that are suitable for the application, and of course the process for design implementation. A key goal for any data center operator is of course uptime. Now a significant contributor to ensuring uptime is detection, and that is the ability to overcome variables and detect before critical fire sizes is reached, allowing personnel the time required to control the situation and of course mitigate the consequences. There are 4 stages to fire development, and that is the incipient stage, the growth stage, the fully developed stage, leading up to the decay stage. Now, of course, the opportune time to respond is, of course, in this incipient phase of fire growth development prior to flame and prolonged smoke contamination. It's this stage that makes the difference between turning what would be a firefighting exercise into potentially a maintenance task. Of course, an ideal detection technology would be one that can monitor the entire progression of fire development, providing alarm thresholds at each stage, allowing for staged response leading up to the reliable initiation suppression systems. The unique environments within IT communication infrastructure presents a challenge to both early and reliable fire detection. Conventional and prescriptive methods, technologies, placement, and spacing can be challenging, if not impossible. Selection of particular technology is based on the technology's suitability to effectively perform its intended function within the sensitivity objectives. So sensitivity is a key factor in detecting fires at their incipient stage, allowing early intervention for investigation and action, potentially before smoke and corrosive gases affect equipment and personnel. And sensitivity is also key in overcoming the effects of dilution. Airflow patterns is another consideration within IT communication infrastructure, as it can oftentimes be turbulent, unpredictable, and in directions not conducive to detector placement. And given these dynamic variables, certainty of smoke reaching conventional passive technologies presents performance challenges. So careful consideration should be given to the interrelationship between the ventilation and fire detection systems. A determination as to the common airflow paths, plenums, point of filtration, makeup air entry points, temperature, airflow velocities, and so forth must be taken into consideration. So on the subject of temperatures, within certain cooling configurations, specifically hot out containment, temperatures are exceeding traditional detection technologies listed range, with some industry references reporting as high as 140 degrees Fahrenheit within the hot aisle. So when considering smoke detection within hot aisle containment, this of course limits selection of available solutions. Industry transitions have outpaced prescriptive placement, which have largely been outclassed by technology innovations. In some cooling configurations, there is no possible location to mount traditional spot-type smoke detectors, of course in accordance with their listings or at locations where smoke is likely to migrate. Then, of course, there is this growing requirement for environmental diagnostics and the need for detection technologies to provide more information so that informed decisions can be made, improving operational efficiency, cost, and of course, mitigation of risk. And cost is another factor contributing to suitability of a particular technology. An ideal detector would be one that is efficient to install, easy to maintain, and is future-proof, thus reducing total cost of ownership. So if we consider VESDA aspirating smoke detection for this application environment, we'll find that the technology possesses characteristics that overcome the challenges of IT communication environments. These features and capabilities include sensitivity, and that is, of course, very early warning fire detection, active versus passive detection performance, and that is the ability to actively draw the environment back to the detection chamber as opposed to waiting for smoke to collect and develop and collect at the detection chamber. We provide multiple alarm thresholds throughout the fire development curve for stage responses leading up to suppression interface and suppression release. We're largely unaffected by airflow or temperature extremes when properly designed. Again, there's no electronics in the pipe network, and therefore we can withstand environments that either are high in temperature, high in EMI, RF, and again, the ability to overcome some of those conditions. Cumulative detection performance is a key advantage to aspirating detection technologies in that more than one hole is likely to see smoke, and the effects is that the smoke is then cumulative back at the detection chamber. We provide absolute smoke detection. Once set, the sensitivities remain fixed and provide reliable and predictable detection performance throughout the life of the detector. There's absolutely zero calibration requirements of the detector once installed and throughout the life of its operation. We provide flexibility of various sampling configurations that allow you to set the sampling points at locations where traditionally you wouldn't be able to put smoke detectors, and of course follow smoke where smoke tends to travel and strategically place those sampling points in locations where needed. And of course, as we talk about simplicity, and that is, it provides low maintenance and the ease of maintenance, providing an accessible solution as opposed to one that is inaccessible. And of course, that leads into security, and that is accessibility without disruption of operations. The idea with an air sampling type system, or at least VESTA type systems, is that you test the very last sample port for smoke transport time test, and to meet codes and standards such as NFPA 72, we're looking for transport time from the furthest hole back to the detector, and we're verifying airflow through all other ports by that particular test. We have a documented procedure for doing that, and that's a method in which we greatly reduce the maintenance cost by only having to test the very last sample holes. And when you design the system appropriately, you bring those sampling points to a location that's accessible without the need for special equipment or tools to get to it to test. So on a typical ASD type device, for those of you that aren't familiar with how air sampling type systems work, it basically consists of sections of small diameter pipe with sampling holes drilled at regular intervals along their lengths. You'll have an aspirating fan in the detection unit itself. Some people refer to this as the control panel, but in fact it's nothing more than a detection or detector, if you would. At the end of these pipes, we actively draw air into the smoke through various sample holes towards the smoke detectors. So along the pipe network, we'll have sample holes either drill directly into the pipe or come down with capillary or remote points, which I'll show you in some additional slides as we pass through them. But the idea then is we draw that environment through the sampling point back to the detector, where it then monitors for the development of fire, either in the incipient stage, all the way, as I mentioned, through the entire growth stage of a fire event. So the design, we have to take various conditions and factors into consideration, and that is, of course, the containment type and configuration of the containment aisle, and that is it hot versus cold and so forth. What governing codes and standards require. Monitoring location, that is determining the sampling approach, port locations, the orientation of the sampling points, and density of the sampling points to meet performance objectives. And of course, that leads into product selection, determining which model of detector is best suited or most ideal to be used in the particular application. And then, of course, then leading into the routing of the pipe network and how to achieve getting the pipe from point A to point B. So as mentioned in the previous slide, that it's important to understand the various cooling configurations and containment aisle configurations. If we look at the hot aisle, cold aisle concept, it's an approach where equipment is loaded into data center cabinets such that all air intakes or inlets face the same way, the front of the cabinet, and the air exhausts or outlets, consequently, are facing the back of the cabinet. Furthermore, the cabinets are generally oriented in rows such that the front of the cabinets are in line with each other and the backs are in line with each other. Additional rows are added such that the backs of the cabinets in adjacent rows face each other. This, of course, creates the hot aisle. And in the front of the cabinets in adjacent rows, they face each other. Cold air is forced into the aisles in which the cabinet fronts face each other, creating a cold aisle. You'll have air handling units or crack units located at the ends of the aisles. These units intake air from the room, cool the air by exchanging heat with chilled water, and force cold air back into the room, usually through perforated tiles that allow the air to percolate from a raised floor cold air plenum into the cold aisles. And so as we look at containment aisle, let's start with cold containment aisle. So cold containment aisle is identical to hot aisle, cold aisle, with the exception that cold aisles are closed off and contained with the use of solid obstructions, as illustrated by the blue in this illustration here. The goal of this is to prevent the air arising from the raised floor from mixing with air in the room, providing air to the server inlets that is close in temperature to that supplied by the air conditioning unit. The goal of the confinement is to maximize the utilization of cold air percolating from the raised floor. So opposite to cold aisle containment would be hot aisle containment configuration. Hot aisle containment is used to prevent hot air from the hot aisles from escaping and recirculating to the server outlets. And this is accomplished by adding solid obstructions to close off the hot aisles. Yet in another configuration, we consider the use of Enroll cooling technology, which is based on deploying cooling units alongside of the servers, directly putting cold air into the cold aisle, bypassing the need for a raised floor. In this configuration, the return side of the cooling units face the hot aisles and the supply side face the cold aisle. The goal is to shift the cooling from a room-based approach to a row-based approach. Cooling units are directed towards each other such that they build up static pressure in the cold aisles. The designer must also take into consideration codes and standards. And so if we look at it from a prescriptive approach, that generally will mean open area protection, concealed spaces where combustibles are present, which can include below raised floors or above ceiling voids, enclosed occupiable spaces, and this can include containment aisles, as generally will be classified as occupiable spaces as defined in codes and standards, and then spacing and placement in accordance with the governing code and standard, and sensitivity that is in accordance with the product's listings and approvals. So the design conditions and factors in containment aisles may mean that the recommendations of the current codes and standards may not offer the correct level of protection, and therefore the migration to a performance-based approach deems more warranted in these types of infrastructure. With respect to performance-based coverage strategy, we take the assessment of the risk and performance requirements specific to particular areas within the IT communication facility, which forms the basis for the level of protection applied in terms of location, sample point density, and nominal sensitivity. Now, as we look at the various areas, we talk about open areas, concealed spaces where combustibles are present, and again, that can include below raised floors or above the ceiling. Enclosed occupiable spaces, so again, as we talked about, that could be within containment aisles. Now, increasing placement density and sensitivity improves the chances of detecting incipient low-energy fires before fire conditions threaten services network reliability. And so, with the idea of leading-edge practices, and again, the aim of ensuring uptime objectives are met, the consideration of very early warning fire detection coverage schemes are generally applied to these mission-critical environments. And so as we look at it from a mission-critical environment or very early warning fire detection perspective, we talk about port spacing every 200 square foot in open areas, and we talk about sensitivity objectives at 1% obscuration per foot per port. And then we also talk about monitoring all air leaving the space or compartment, and that generally means monitoring of return air grills or paths along the air distribution to where we can predict where smoke is going to go. And so as we talk about return air paths, that's every 4 square foot of grill area. So that's generally the requirements for very early warning fire detection, or the criteria, I should say, for very early warning fire detection. In terms of coverage strategy, there are various degrees of sampling configurations that can be applied in any given application, each having a certain impact to cost. Elimination of any given point introduces compromise. A performance-based scheme will consider multiple locations. All right, well, let's apply some coverage strategy to various scenarios of cooling strategies, and we can't cover all of them because there's so many variables and so many variations, but we'll cover the most obvious. And starting with hot aisle, cold aisle, in this particular scenario, we show a space that's open to the deck, and as you can see here, what I've done is laid out my pipe network such that I'm placing my rigid pipe to the underside of the deck. I'm drilling holes directly into the pipe. I'm facing those sampling points towards the finished floor. I'm spacing my sampling points in accordance with a protection objective of 200 square foot on center, and planning my alignment above the hot aisles. Now this considers a very early warning fire detection scheme. So with that, my target transport time is 60 seconds or less, and my target sensitivity at each and every port is 1% obscuration per foot. Now, in this configuration here, I'm bringing the pipes back to a centralized detector. So this might be, for instance, one VLP, one Vesa Laser Plus detector, covering this particular space. Now, let's assume that in this particular scenario, we now have a drop ceiling, and the objective is, in this particular case, not to see the pipe below the ceiling. So in which case, we're going to mount the pipe above the ceiling to the underside of the deck. Now we're going to take some strategic use of remote sampling points. In this configuration, what I've done is I essentially cut the number of detection units in half, ultimately, depending on how big my space is. The fact is I've got less pipe to install, I'll have less power supplies to install, and I reduce my labor cost, and I'll ultimately reduce my maintenance cost, thus improving my total cost of ownership using this strategy. And so what I've done with the strategy here is I've taken my main pipe trunks, I positioned them strategically above the rows, and I'm now taking my capillary drops, and I'm using the use of flexible capillary tubing to interconnect remote sampling points that I'd mount to the bottom side of the drop ceiling to interconnect with my main pipe trunk. And in this fashion, I can go up to 26 feet worth of capillary drop on either side, positioning my sample points where I need them. So I'm providing the same coverage as I had in my previous scenario, but now I've got less pipe and strategic use of the sampling points in this configuration. So that's just one method in which you can take some advantage of working with a drop ceiling. Now, let's now consider As I mentioned before, performance-based approach considers multiple paths for detection or location of detection. And in this case, what I've done in this scenario is I've laid in pipe directly at the face of the return air grills of the crack units. And the idea is that I'm going to detect any smoke that's not making it to the ceiling is being migrated to the return paths of the air handling units, and I'm detecting it before it gets into the air handling unit, filters, and gets further distributed back into the space. So in this scenario here, I'm following right out of our mission critical design guide, which talks about return air coverage, and that is sampling points spaced every 4 square foot of grill area. I'm achieving 1% obscuration per foot at the sampling point, and I'm setting out to achieve less than 60 seconds transport time at the furthest end of each pipe run for each air handling unit. And the intent there is, again, a very early warning fire detection scheme, a performance-based scheme. And it's very important in this application to consider the orientation of the sampling points such that I'm not directly facing the sampling points towards the incoming airflow. I'm actually angling them, orienting them 20 to 45 degrees downward towards the incoming airflow. And this will help avoid any influence that the air handling systems may have or the air currents may have on pressure differentials or airflow faults at the detector. So that's an important factor to avoid airflow faults at the detector, and it'll improve detection performance in that respect, regardless of the operating parameters of the crack unit, whether it's cycling off or on, or the variable drive. So the other consideration is also the distance off the face of the grill for my sampling pipe, and I want to be 2 to 8 inches from the face of the grill in order to avoid the low pressure point directly at the grill surface. So that kind of covers the approach in terms of my return air monitoring within this given space. So concealed spaces such as the raised floor and sometimes ceiling voids of IT communication facilities may contain large quantities of electrical cabling. In such cases, it's important that these areas are protected. And when used for return and supply plenums, the presence of high airflows in these concealed spaces will lead to rapid spread of fire and smoke. So the method of detection involves placement of sampling ports within the concealed space, oriented downwards, and again, where the space is used as a return or supply air plenum, orient the sample points again 20 to 45 degrees downwards towards the incoming airflow, will further assist to counteract pressure effects. Plus, it'll also prevent buildup of dust and dirt by orienting them downward, again 20 to 45 degrees. As mentioned earlier, for open area coverage, sampling points are spaced in compliance with the sensitivity objective. So for very early warning, that would be every 200 square foot. And again, construction is generally 3/4 inch CPVC piping, supported every 5 foot, labeled in accordance with NFPA 72. And if the space is classified as a plenum, ensure that all materials are approved and listed for plenum use. Now, generally what we'll do in this type of application, because the pipe is concealed, and again, we want the ease of maintenance and accessibility, is we'll bring a test point or benchmark test point up from the raised floor or down from the return plenum to an accessible location above finished floor where we can easily get to that sample point or benchmark test point for test and inspection on an ongoing regular basis. So now let's consider a cold aisle containment coverage strategy, and starting with the open areas. In this configuration, or the scenario, as you see, I've got my sampling pipe very much similar to my previous design for hot aisle, cold aisle without the containment, positioned in the open area. And in this scenario, my ceiling is open to the deck. I'm placing my sample points directly to the bottom side of the deck, facing downwards towards the finished floor. And meeting a very early warning fire detection objective, I'm placing my sample points every 200 square foot of area, and I'm achieving a 1% obscuration per foot at the sample point with 60 seconds or less transport time. So it looks very much like the previous scenario I've shown you, with the exception that now we've got these enclosed spaces, and need to consider those where they're considered occupiable and where detection will be required. So there are a variety of ways that I can actually cover the enclosed spaces, or in this case the cold containment aisles. And this is just one scenario, but the idea is that my sampling arrangement, if I'm following again the very early warning fire detection scheme, needs to be every 200 square feet. So what I'll do in this respect is plan my sampling point configuration and then plan on how to get my pipe to it. Now in this consideration or configuration, I've actually taken the sample pipe dedicated to the cold aisles and placed them directly above the hot aisle, or pipe monitoring the hot aisle. And what I've done then is taken the capillary tubes and come off either side of the pipe into the cold aisles. So again, I'm making effective use of that capillary tube as described before, and thus limiting the overall number of detectors that would be required to protect the space, or the number of runs of pipes that I'd have to run to protect this space. So that's an effective use of, again, capillary tubes to monitor the cold aisles in this scenario. And again, meeting the same objectives: 1% obfuscation per foot, 60 seconds or less transport time, and that's my design scenario approach for this particular scenario. And again, since I'm following a performance-based approach, I want to consider the protection of return air paths, or air leaving the space, and in this case, positioning my sample pipe as I have in the scenario before, right at the face of the return air grills to these particular crack units. And again, every 4 square foot of grill area, 1% obfuscation per foot, and 60 seconds or less is the criteria. And as described earlier in my previous scenario, where I do have concealed spaces and there are the presence of combustibles, or I'm forming part of a suppression system, my detection scheme will cover the return plenum as well as the supply plenum. So below, in this scenario, below the raised floor and above the ceiling. And again, following that 200 square foot sample point scheme, and 1% obfuscation per foot and 60 seconds or less transport time. So now let's consider a hot aisle containment coverage strategy, and where here in this scenario I'm showing something very similar in terms of a facility having a drop ceiling. And in this case, I'm containing the hot aisles with the hot aisles connecting all the way up to the drop ceiling, and above the drop ceiling is the hot air return plenum. And in this scenario, I'm placing my sampling pipe directly above each hot aisle. I'm drilling my sample holes directly into the pipe network, and I'm orienting them 20 to 45 degrees towards the incoming airflow. Now in this case, I want to have some addressability. I want to be able to identify which individual row is affected. So in this case, I might consider the use of a VESDA laser scanner, and in that respect, I'm able to identify the individual row and direct personnel to the affected row as opposed to somewhere on the data floor. So that's the design approach in terms of the pipe network and the sample hole arrangement. But now let's talk about some of the design goals with respect to port spacing and sensitivity. Now, sensitivity is going to very much follow the similar approach in terms of very early warning fire detection. That's 1% obfuscation per foot at the sampling point. My transport time is as well less than 60 seconds or less. And I also want to consider test points, bringing down test points below the ceiling to an accessible level above finished floor for annual test and inspection without having to get above the ceiling and disrupting the facility. So all that takes into consideration. But now I'm also considering my port placement less than 200 square foot, simply because I'll treat this as somewhat of a return air path. Now, we have quite a bit of experience in high airflow environments, and in fact have an application guide specific to, say, a clean room where the air velocities are quite excessive, and we have some guidance with respect to port sensitivity based on air velocities for very early warning fire detection schemes, and at return air paths, which falls outside of the criteria of any codes and standards, but more so towards application experience and our own in situ tests and performance criteria. So in this case, I've reduced the spacing from 200 square foot down to 10 square foot within my hot aisles. So I'm not quite as aggressive as a return air grill per se, but I'm not as relaxed as, say, 200 square foot in these particular applications. And the reason for that is I don't want to miss the migration of smoke past the pipe and into the plenum. So I want to be sure to detect it, and the best way to do that is decrease my spacing in this particular scenario. So as we discussed the hot aisles being protected, we also got to give consideration to the cold aisles, or the open areas in this case. And so very similar to my previous design approach, I've placed sampling points everywhere where I need a detector. And in this case, if I'm following very early warning fire detection scheme, every 200 square feet of floor area I'm protecting, or open area I'm protecting with a sampling point. And again, this strategic use of capillary tubes comes in handy in this approach, where I'm mounting my pipe above the drop ceiling. I'm positioning my pipe directly above the pipe covering the hot aisle, so that way I can strategically go either side of the racks into the cold aisles and monitor the cold aisles off the pipe network serving the cold aisles. And so in that fashion, you can see again I've taken some efficiencies out of use of capillary tubes and provide a very effective coverage scheme for the cold aisles, effective and cost effective in that respect. So here I've actually mapped in sampling pipe at the return air paths leading to the individual crack unit serving the space. And this would serve somewhat redundant to the detection at the individual hot aisles. But the idea here is I perhaps provide N+1 redundancy, or where I do have the risk of potential risk of combustibles in the hot air plenum. I can detect an occurrence happening within the hot air plenum. Another placement of the sampling pipe might very well be at the supply side of these crack units. So in that respect, anything coming into it, I'll detect. And then, of course, if there's an actual event within the crack unit itself, I can detect that and provide indication early enough before smoke migrates and further distributes throughout the entire data hall. So that's maybe another consideration, is the supply side of the crack units. But in both respects, I'm going to cover every 4 square foot of grill area, and again meet some of those sensitivity and transport time objectives that I had before for very early warning fire detection. Now, as noted before, where I do have combustibles below the raised floor or above the ceiling, or I'm forming part of a detection system for suppression release, I'll place my detection in these particular concealed spaces based on the sensitivity objectives I'm trying to meet. So again, for very early warning fire detection, every 200 square foot I'll place a sampling point. And again, where these are used as return or supply plenums, I'll orient the sampling points 20 to 45 degrees towards the incoming airflow, and meet that 1% obscuration per foot in 60 seconds or less transport time, and cover the space effectively in that approach. In-row cooling units are another configuration of cooling strategies deployed. And in this particular configuration, for reliable, very early detection of smoke concentration, you want to position VESA sampling points at the rear of the server cabinets at the point where the air exits, or at the inlet of the in-row coolers themselves, similar to what I've illustrated in this picture. You'll treat these very similar to how you would return air paths, in that you'll provide sampling every 4 square foot of grill area, and you'll orient the sampling points approximately 20 to 45 degrees towards the incoming airflow, and you'll set out to achieve 1% obscuration per foot per sampling point for very early warning and 60 seconds or less transport time. And the use of unions would be very practical in this application. Of course, being able to remove the grill and remove the pipe with it is one method. And there's a variety of configurations that you can consider in terms of construction of the sampling network. And we've seen the use of flexible tubing as opposed to rigid tubing used, integrated into the actual grill itself, and just a variety of techniques that you can use to position those sampling holes. But again, the idea is every 4 square foot of grill area to effectively cover the migration of smoke from server cabinet to server cabinet and to cooling unit, and distributed throughout the row. Here's a different illustration of that shown from a plan view of the coverage scheme. So as I mentioned, 2 scenarios. Either at the inlet of the in-row cooler or at the outlet path of the server rack, positioning your sampling pipe again such that you're placing a sample point every 4 square foot of grill area. So yet another configuration, as I mentioned, there's a wide variety of cooling configurations and cooling strategies, and this is just one more of them, and that's the use of overhead cooling units. And so in this illustration, what I've shown here in this sampling pipe positioned at a common collection point before the hot air leaves and enters into more or less this plenum and enters either side of the cooling units. And that's one configuration. The other configuration might be to place the sampling points at the supply side of these cooling units, and therefore I can detect an occurrence or a failure mode within the cooling units before it's redistributed back into the equipment cabinets or prolonged exposure into the equipment cabinets. So I'm detecting it at this location as opposed to this location. I'm also showing that I've got area detection. The idea is that I also want to provide area detection to the extent that I'm covering the area in accordance with the sensitivity objectives that I selected for the space, such as 200 square foot per sampling point for the open areas. Now you'll see coverage at the HVAC unit, and this HVAC unit is largely used for humidification of the area, but monitoring at this point provides, again, a cost-effective redundancy, or N+1 redundancy, if you look at it from that perspective. So a variety of monitoring locations that I can consider in this configuration or scenario here. But as I pointed out here in this respect, if I'm treating this as a return path or a supply path in this matter, so I'm going to place my sampling every 4 square foot of grill area and achieve these design goals: 1% obscuration per foot at the sampling point, in 60 seconds or less transport time from the furthest port on the pipe network. Once site conditions are known and coverage techniques selected, the designer must identify the appropriate VESDA detector model best suited to meet the project requirements. Selection criteria should include consideration to coverage capacity, and that is selecting appropriately sized detector that best suits the coverage area or object being protected, ensuring efficiencies are achieved. Also, addressability, and that is to meet specific zoning requirements, or the need for communicating over a network, or is it standalone operation. With over 10 detector types and 40 plus configuration possibilities, Xtralis by far has the widest range and variety of detectors in the industry, providing for scalable solutions that are suited for their intended application, thus allowing for efficient and affordable installations. With respect to coverage capacity, this particular chart illustrates our various detector models, placing them on the chart in terms of their area coverage capacity. And so starting on the far left, we find the VLQ, VESDA Laser Quantum, which is our newest release. And this particular detector is a 2-pipe inlet detector with a capacity of up to 20 feet per pipe, giving you the capability of providing up to 4 sampling holes, 2 per pipe network, to cover areas as large as 1,000 square foot. The next detector is the VESDA Laser Focus, and this particular model is a VLF 250, which is UL listed up to 2,500 square foot of coverage, 12 sampling holes. It's a single inlet detector. Its counterpart, the VLF 500, is UL listed for 5,000 square foot coverage. It also is a single pipe inlet detector, good for up to 24 sampling holes. And then moving on up to the VESDA Laser Compact, the VLC, which is also a single inlet detector, UL listed for up to 8,000 square foot of coverage and up to 40 sampling holes. Now the VLC comes in 2 variants, one with the network and without the network capabilities. So the VLC 500 is without the network, and the VLC 505 is with network. Now the next detector model lineups is the VLP, VESDA Laser Plus, the VLS, VESDA Laser Scanner, and our newest release, the VEU. Now these detectors are UL listed for up to 20,000 square foot of coverage. All 3 of these detectors have 4 pipe inlets and can have as many as 100 sampling holes, but that depending on your Aspire 2 calculations in terms of the area coverage and your sensitivity objectives and your transport time objectives. But now the difference between the VLP and the VLS is that the VLS is the Vessel Laser Scanner is again, as I mentioned, a 4-pipe inlet detector, but each pipe is considered a zone and can provide addressability to the individual pipe. Now, the latest release is the VEU, which provides a whole host of new features and functions over our previous models. And this particular detector also offers various functions such as analytics. It has a built-in analytic engine, which you can then bring in various modules, allowing you to do different functions in terms of monitoring for analytical information about the environment. It provides you the ability to have Wi-Fi, Ethernet connectivity, remote communications via tablets, higher sensitivity capabilities in our previous models, up to 15 times more sensitive, different means of operating in terms of its detection chamber. Using CMOS imaging, we can collect more information, provide more data points, and thus run the analytic engines, providing more information about the environment. So a whole host of new features, and I encourage you to inquire with us about the capabilities and functions of this new detector if you haven't seen it yet. But it is really the next generation of ASD, rare sampling detection. Pipe and fittings form an integral part of an aspirating smoke detection system. Consideration must be given to the type of material, ensuring material selected is fit for purpose and approved for use by local building codes, has a low flame smoke spread, and when used in plenum spaces is plenum rated dry and listed with the detector, is labeled in accordance with codes and standards such as NFPA 72, uses appropriately listed fasteners, and can be sealed and permanently fixed in accordance with local codes and standards, again, such as NFPA 72. Now, Xtralis offers a whole lineup of various pipe fittings, remote sampling points, capillary tubing, essentially everything you need to complete a particular project. And our particular pipe is CPVC. It's UL listed, again, dry with the detector, and it's pre-labeled "Do Not Disturb Aspirating Smoke Detection System" in accordance with NFPA 72, so it provides the convenience of pre-labeling. And essentially all of our fittings meet the requirements for plenum rating. Now, consideration must also be given to remote ancillary items, which can contribute to the efficiency of installation and effectiveness of operation by placing components where needed for the ability to view status, program functions, and manage all aspects of the system remotely. Some examples of ancillary items include display modules, which either can be integral to the detector or remotely mounted, programmer modules, again, which can be integral or remotely mounted, relay modules, which can sit on the network and position your relays remotely, which can either be built into the displays, remotely mounted, or individual modules that just contain the network relays. And of course, the ability to manage the system via remote PC management, and that's our VESA System Management 4 software that provides that capability. The designer also has to consider interface to other systems, such as the building fire alarm control panel, suppression control panel, or building automation system. Now, there's various methods of interfacing VESA systems, such as the use of relays, and that is either on board, or the relays can be remoted using a network relay card, for instance, or having the relays actually fitted into the remote display, as an example. Now, VESA detectors also have an intelligent interface with various manufacturers' fire alarm and suppression control panels, and in that method you'll have a UL-listed interface that provides intelligent information between the fire alarm control panel or suppression control panel, providing more information and the reliability of a communication path as opposed to relay connectivity, and there's a labor savings factor contributed to that as well. Now, the various alarms that you'll interface range by detector, but here's an example of 4 levels of alarm, and that is alert, which oftentimes can be supervisory signals, action, which is oftentimes considered the pre-alarm level, which again is oftentimes considered supervisory, the fire 1 threshold, in which case this is the threshold that generally initiates a fire alarm condition, sounding the knack, and allowing personnel to take action. And then as the progression of fire develops, the fire 2 threshold is oftentimes used for suppression interface or fan control, fan shutdown, for instance. So a variety of alarm functions for staged response. Now, VESA system management software, as we mentioned in the previous slides, is available to where you can provide a management platform that monitors the entire network of detectors and can monitor multiple networks across not just the facility or the campus, but across multiple campuses or multiple facilities, for that matter, anywhere in the world. So a quite powerful package, and we won't go into all the bells and whistles of VESA system management, but there are quite a few, and I encourage you to look into it because it does provide a means to centralize management of a particular network of detectors should you have a large number of detectors being networked. Well, we've covered quite a bit in the slides presented, showing you a number of application scenarios and guidelines. As mentioned earlier on, the scenarios weren't exhaustive for each variation. The coverage strategies, however, are somewhat universal. Containment aisles do a good job at channeling air, and it's this attribute that makes smoke migration and sampling point placements predictable. So in closing, I want to emphasize that a properly designed air sampling smoke detection system is paramount for the proper operation of the system and in meeting fire protection objectives. Design and specification should take into consideration qualifications of designer, installer, and commissioning technician, applying coverage techniques that account for all possible smoke migration paths, maximizing coverage by utilizing combined coverage techniques where possible, never exceeding limitations specified in product data sheets, ensuring system design meets the manufacturer's criteria and local jurisdiction requirements, and including manufacturing in early stages of project work and design reviews. Well, that brings us to a close. Once again, thank you for attending our webinar. We hope you found the information beneficial. For more information on applications of VESA in IT communication infrastructure, and more specifically within containment aisles, be sure to review our design guides. Also, if you'd like to discuss a specific application, please contact an Xtralis regional manager or myself using the following email address or phone number. Again, thank you.